Hello, welcome back. Today let's try to solve another Leetcode problem 684, redundant connection. Let me explain the problem a little bit and then go to the code editor to finish the coding. So we are giving a tree data structure, but for this tree, there's another two nodes which are connected. For example, this is 1, 2, 3, and 1 to 2. They are tree data structure, but there's also another node which is connected. We need to find this actual node, which means if we can remove this the direction, we can remove this ends from the node 2 to 3 or 3 to 2. So we're gonna get a tree data structure. So we're gonna return 2 and 3. Yeah. So a tree is an undirected graph that is connected and has no cycles. But now we have a cycle because 2 and 3 are connected. We just need to find the actual edge for the graph. For example, for this one, so for 1, 2, it is okay, 2 to 3, it is okay, and then 3 to 4, it is okay. But 1 to 4, it becomes a loop, and this is the last, so we're gonna return a 1 to 4. For 1 to 5, it is still okay. And we need to return an end that can be removed so that the resulting graph is a tree. So we need to find that one. Yeah, and for this problem, I'm gonna use unified because unified is really easy to solve such kind of a connection problem. So for unified, I'm going to check. So if first I'm going to check 1 and 2. If 1 and 2 are not connected, I'm gonna connect 1 and 2. And then 1 to 3, I'm gonna connect 1 to 3. But when it comes to 2 to 3, it means 2's parent is 1, 3's parent is also 1. It means 2 and 3 has already connected. If 2 and 3 has already connected, I'm gonna return 2 and 3 directly. So this is the idea. Actually, it is not so difficult. Now let me go to the unified. For unified, I'm gonna define a UF array. This means my unified array. And also we need to take care the nodes is starting from 1, not from 0. So I'm going to use I for I in range. So how many vertices? The vertices is equal to the ends because there's always an actual ends for the tree data structure. If there's an actual ends, it means the ends number of ends equals to the number of vertices. So inside, I'm going to use the length of ends. This means the number of vertices, but I need to plus 1 because we need to use 1 to 3 for this example. We need to use index 1 to n for our unified. Actually, for the 0, we don't need it, but we can keep it like this. This means I is starting from 0 to n. Yeah, so the index will have 0 to n. So this is why we're going to define a unified array like this. Now I'm going to define the find function. So for the find, I'm going to give a number n. I'm going to find this node. So this n, I'm going to have a tag. So while unified uf n not equal to n, so n should equal to ufn. And I'm going to check this. So if it goes out of the loop, I'm gonna just return this n node. And then I'm going to define the union. So the union will be two nodes n1 and n2. So it will be the uf find n2. First, I'm gonna find the parent of n2, and here I'm gonna find the parent of n1. So here this means n1 is the parent of n2. It means they will be connected. So if there is a union, for example, union 1 and 2, it means 1 and 2 will be connected. If it is union 1 and 2, and so 2 will be, so 1 will be the parent of 2. So this is the union. Now I'm going to do my last tag. So for u, v in edges. This means I'm going to check the edge by edge. So the first edge is gonna be 1 and 2. So I'm going to check if find u not equal to find v. This means for these ends, if they are not having the same parent, it means if they are not connected. So I'm going to connect it. So connection is for union. So I'm going to use union, U and V. Else, it means if they are already connected. For example, if I go to 1 and 2 connected, 1 and 3 connected, then I will go to 2 and 3. Because 2 and 3 has already been connected, because 2 to 1 to 3. Now, I'm just need to return the result, because the result is an array for the two vertices from 2 to 3. So this is gonna return U and V. So for the time complexity, this is just ON. Because for union find here, I didn't use the path compression. If I use path compression, here the find gonna be O1, and here the union, because union gonna use the find, it will also be O1. Now let me run it to check if everything works. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it's pretty fast, and it passed all the testing cases. So here, I just needed to, yeah, if I would like to end the path compression. Now let me end the path compression for the find. I'm not going to use racking for the union, but I'm going to put the path compression into the find. So I'm going to change this n variable to the root. Yeah, because I'm going to use n later for the path compression. So here, everything gonna be the same. I just changed these variables to the root. But here, before that, I'm going to use n variable as my root. Now I'm going to use the path compression to compress the path. So I'm going to check while this n not equal to the root, because here while use the while loop for these two lines, the root may change. Yeah, but here this n may not equal to the root. If it is not equal, I'm going to check. So I'm going to have a next variable. This next will be uf n, and then I'm going to compress the path. So how can I compress? So inside of the uf array, the union find array, this n should be pointed to the root. So this means I've already compressed. And next, I'm going to use this n equal to the next. The next is for the next node. For example, if it is a linear, let me see if I can find an example from here. Yeah, it would take some time, but I will go back later. Let me just check if it can improve the speed. Now let me run it to check if there are any mistakes. Yeah, I hope there's no infinite loop. It is okay. Now let me submit it to check if it can really improve the speed. Yeah, as you can see, the speed improves a little bit, but just because this time has already been so fast, there's not so clear difference. But actually, for this one, it is just one time. It really improves the speed. Now let me go to the whiteboard to explain a little bit about why we need the path compression. So for here, for the normal union find, if in some cases, it may have a linear. For example, this is the node 1, this is the node 2, and the node 3, and the node 4. It is some linear. If you need to find node 4, it will go to 3, 2, and 1 because its parent is 1. It takes on time. But when you use path compression, so the 2 will be pointed to 1, and 3 node will be directly pointed to 1, and 4 will be directly pointed to 1. So when you're gonna check find 4, so its parent is 1, you're gonna just use O1 time. So this is why we're gonna use path compression for this 4 lines of code. It's really important because for some cases you cannot pass in Leetcode. Maybe the time limited exceeded, and then you can use the path compression. But for most of the cases, I think nearly 100% of the cases you don't need this, but you should know a little bit about the path compression. Thank you for watching. If you think this is helpful, please like and subscribe. I will upload more Leetcode problems like this. See you next time.